All right, welcome back to our Chapter 4 series of videos for our zinc state physics class. And I was right in the middle. We're actually very nearly done with this example 4.7. This is a fairly simple example, but it does illustrate an important concept. And that is the acceleration caused by an imbalance of forces. We're just simply asking what happens if we have a box that has a weight of 98 newtons and we pull up on it with a force of 100 newtons. It should be pretty obvious that if you pull up on something with a force greater than its weight, you will lift it up. And that's exactly what's going to happen. We have an upward force of 100 newtons, a downward force of 2 newtons. So the sum of forces is positive 2 newtons. So we have two different forces, but when we add them together, we end up with a net upward force. And if force equals mass times acceleration, and we have an upward force, that means we're also going to have an upward acceleration. So if we recall that F equals mg, that's weight, the force of gravity, so I could put a subscript g there, Fg, the weight of due to gravity is mg, and we were given in the problem statement this box has a weight of 98.0 newtons. That'd be mass times the acceleration due to gravity is 9.80 meters per second squared. Then we can determine that the mass of the box is 98.0 divided by 9.80, which means it has a mass of 10.0 kilograms. And so if our upward force, our net force, our sum of forces is 2 upward, positive 2.0 newtons equals the mass of the box, 10.0 kilograms, times acceleration, then we can solve that equation for acceleration. A is equal to 2.0 newtons divided by 10.0 kilograms, and we end up with 0.2 meters per second squared is the acceleration. That's how quickly the box will accelerate upward when we apply this 100 Newton force to it. And I'm realizing I was a little bit sloppy here with my significant figures. So if we look at the data that was given to us, 100.0, that's 4 significant figures. 98.0 is 3. So our final answer should have 3 significant figures. So this really should be 0.200 meters per second squared. I suppose if I'm going to require you to be careful about your significant figures, then I should do the same. Okay, let's move on to solving problems that are a little bit more complicated than the one we just looked at. So the problem we just did is pretty simple because both of the forces were on the same line of action. We had a box, its weight was going straight down, and we were pulling up on it straight up. But we need to be able to solve problems involving different forces that are applied at any angle. In fact, we will actually do this example problem here in a couple slides. But the basic strategy to follow is, first of all, draw a sketch. Absolutely, wholeheartedly agree with that. You got to draw a sketch, I feel, to really understand what's going on. And then draw what's called a free body diagram. So a free body diagram I would describe as just a simple drawing, a simple diagram that shows all the forces that are acting on an object. Like here, for instance, this diagram that I drew based on the previous problem. I just drew a square to represent the box with an arrow down representing its weight and an arrow up representing the force that we were applying to it. And I didn't even necessarily need to draw the shape of the box. I could just represent any object, like the box, with a dot, with a force down and a force up. Free body diagrams do not need to be artistic. They don't need to necessarily represent the way the object actually looks. What's important is to represent the forces. The forces are primarily what we're interested in. And they don't necessarily have to be to scale or at the right angle, but the more accurate you can make them, the more it helps you to visualize what's going on. Anytime you're presented with diagonal forces, your immediate thought should be, I don't like diagonal forces. I want to change that into a pair of vertical and horizontal forces. So in other words, resolve or break them down into their vertical and horizontal components. Okay, and then we can apply Newton's second law in the x direction and the y direction, and by setting up a series of equations and then solve. And this may require the solving of two equations simultaneously, solving a system of equations. So let's do this example here with the boat. This boat is being pulled in to dock by these two gentlemen wearing the different colored hats, and they are pulling with different forces and at different angles. Now that's potentially going to cause an issue. If they really wanted this boat to go straight ahead, their best bet would be to both pull with the same amount of force at the exact same angle. They're not doing that, however, so we want to find what is going to happen to this boat. Is it going to drift up? Is it going to drift down? What's going on? So we've got the diagram. We don't need to sketch the diagram. It's pretty much given to us. So the next thing we need to do is find the x and y components. We need to break down these vectors into their vertical and horizontal components. So if we start with FA, the x component of that is going to be the magnitude of the diagonal vector FA times cosine of the angle that it makes with the horizontal. So that's a horizontal line. So that is theta sub x for angle A. It's 45 degrees. FA in the y direction is going to equal FA times sine of 45. For force B in the x direction is going to be force B times cosine of, now this one's at a different angle, force B is at an angle of 37 degrees. And force B in the y direction will equal force B times sine of 37. Okay, so force A was 40.0 newtons. I'll write it above. We'll go 40.0 newtons times cosine 45. FB is 30 newtons. 30.0 newtons. Put that in parentheses. Cosine of 37. This again is 40 newtons times sine of 45, and this down here would be 30.030, not 3, 30.0 newtons times sine of 37. Okay, so I wrote that all out, but I already had it typed up. I had it here on the slide. If I just advance the slide, brings this up. Let me actually erase some of the stuff that's getting in the way. There we go. So that's a neater representation of what I just did. So 40 cosine of 45, that gives us 28.3 newtons. For the x component of force A, 30 cosine of 37 gives us 24 newtons is the x component of force B. And if we add those two together, 28.3 plus 24, our resultant of these two forces is going to have a magnitude of 52.3. In the y direction, 40 times sine of 45 is 28.3. So this guy is pulling the boat up, and his upward force is 28.3 newtons. We have to remember this guy is pulling the boat down. So it's really important not to forget this negative sign here. When we find the vertical component of force B, it's negative 18.1. So 28.3 minus 18.1 is 10.2 newtons. So we can see that it has a positive net force, positive 10.2, which means that this guy in the blue is pulling the boat up harder than the guy in the orange is pulling it down, and so the boat is going to end up drifting and hitting this side of the dock if they continue to apply these forces. So this diagram illustrates the x and y components of the resultant. If I flip back here, we found that the resultant has an x component of 52.3 and a y component of 10.2. So I've got 52.3 and 10.2. Those are the two components of the resultant vector. But we would like to describe the vector by giving its magnitude and direction. So these two components, when put together with the resultant, essentially form a right triangle. And so we can find the length of the hypotenuse, which is the magnitude of the resultant, by using Pythagorean's theorem. Pythagoras' theorem, the Pythagorean theorem. So that would be F sub r, the force, the resulting force, would be the square root of 52.3 squared plus 10.2 squared. And that's going to give me 53.3 newtons is the force. And then to find the direction, which we will describe using this angle, theta equals inverse tangent of the opposite over adjacent side. So this is 10.2, this is 52.3, this is the opposite side, 10.2. The adjacent side is the 52.3. So inverse tangent of 10.2 over 52.3 is 11.0 degrees. So that's the magnitude and that's the direction of the resultant. And it looks like I'm nearly out of time again. So this is actually a good stopping point. We'll pick up with section 4.7 in the next video.